Daniel Brennan used to be talk about fiber
Well, yeah, so thank you very much for the introduction. Thank you very much to the organizers for organizing this great conference. It's great to be in Edinburgh. It's a really cool city. Yeah, so today I'm going to tell you about some work I've been doing over the past few years, including a paper with a graduate student, Aidan Scheckler. And it's going to be generally about the topic of symmetry and force gaplessness. And in particular, I want to focus on well, I'll tell you what it is, but it's going to have an emphasis on what I'm going to call generalized symmetry structures. So I think everyone in the room is pretty familiar with what generalized symmetries are. We sort of started many years ago with this idea of like group-like symmetries, including higher form symmetries. And we think about them as acting on charged operators by topological symmetry operators, symmetry defect operators. But now we sort of come a very long way, and we have this entire structure, which we now call categorical symmetries, where the topological operators are no longer sort of dictated by a group structure, but have more of a categorical flavor to them. And so there are many benefits, especially with the application to studying quantum field theory, of these symmetries. So the point is that if you have new symmetries, then you can study what's called the renormalization group flow, and it gives you very strong constraints. And when you have new symmetries, you can also ask whether they have new anomalies. And these give very, very robust constraints. And one of the nice benefits of saying of this new paradigm that we have, that symmetries correspond to topological operators in a theory, is that there's been a lot of work in the math community on topological quantum field theory. And because of this, we're able to make a lot of progress on sort of understanding how anomalies interface with topological theories. And you can use these to prove what are called Lieb-Schultz-Mattis type theorems, or in the high-energy theory community, it's more often called symmetry and force gaplessness. So here's the general idea of what symmetry and force gaplessness is. So first, imagine you have some quantum field theory, which I'm going to call T sub UV. And so the idea, the sort of general paradigm of the renormalization group flow is I start with some conformal quantum field theory. You can think of that how you want. And then what you do is you deform your theory by some sort of interaction, which has some sort of scale associated to it. And then what you do is you go to very low energies and you see what happens. Low energies compared to this interaction scale. And usually what happens is your starting conformal field theory flows to some other sort of conformal field theory, which I'm going to call TIR. So UV is sort of this short distance fundamental scale theory. And this IR is a sort of low energy effective theory. And the process that takes this from one to the other is called the normalization group flow. So if you have a symmetry G, which acts on this theory, and an anomaly of this symmetry, which I'm going to generally denote by this curly A, then the question you want to ask is, how does this constrain the renormalization group flow from some UV theory to some infrared theory? And so there's many ways, many sort of features you can use to distinguish the infrared theory. You can ask if the infrared theory is gapped or if it's gapless. So gapless theory is a generic conformal theory, where the gapped theory is a topological quantum field theory. And then you can ask if the symmetry group G is either if the vacuum is preserving the symmetry or if it spontaneously breaks the symmetry. And so the question of symmetry and force gaplessness is the question of if you have a symmetry with this anomaly, under what conditions must the theory be gapless? So, there's some very old results about what happens for continuous higher form symmetries. And essentially the point is if you have a continuous higher form symmetry with an anomaly, then necessarily leads to a gapless phase. This is some old result by Coleman and Grossman. And but for discrete higher form symmetries, the situation is much more complicated and interesting. This was studied recently by papers by Cordova and Omori. And what you can show is that what they showed rather is that under certain conditions, anomalies can imply that the theory is gaplessness, or that it has to flow to a gapped theory with spontaneous symmetry breaking. So I want to ask a slightly different question, which is very related, is that has to do with what I'm going to call generalized symmetry structures. So in general, in quantum field theory, you can have backgrounds which are like sort of flux backgrounds, which are activated by well, which are not necessarily activated by topological operators. And sometimes you need to go to these special backgrounds in order to activate an anomaly. So one example is if you have spin G structure. So this is when your theory, all of the fields in your theory transform under some symmetry group G. And you can actually, there's -1 inside of this symmetry group G, which is identified with -1 to the F inside of the Lorentz group. And if you do this, what you can do, if all of the fields transform faithfully under this group rather than G times spin D, then you can twist by the C2 symmetry. And that allows you to put the theory on a non-spin manifold by turning on a discrete flux inside of this group G. And so there are some anomalies that can only be activated when you realize that there's this spin G structure. And so what we're going to find is that the anomalies that are related to this structure are going to say something about symmetry fractionalization in the infrared. Another generic sort of background you can have is if you have some zero form symmetry with a non-trivial pi1, then in general you can couple to G bundles, or rather G0 bundles that have an obstruction class for lifting to G tilde, to the universal covariant. And so this is what I mean when I'm saying there's some discrete flux. I'm just saying that you're turning on an obstruction class for this lifting. And there are also cases where this you need to go to these backgrounds to realize anomalies. And this is going to be related to what is sometimes called color flavor symmetry. It's not really a symmetry, it's more just a this is why I want to call it a symmetry structure. In a sense, I want to say something is a symmetry structure if you're allowed to go to some specific backgrounds that are not themselves activated by a symmetry effect operator. And so these are two of the types of symmetry structures I want to talk about, consider in this talk. And the last one is going to be really what I'm going to call coupling constant anomalies. And the idea here is you have some family of theories which are indexed by some periodic parameter, which I'm generically going to call theta. And if the theory is identified with this, you say that the theory at theta is identified with the theory at theta plus 2 pi, then you can compare their partition functions. And if you find that they differ by a phase, then this is often called a coupling constant anomaly. And this is also sometimes related to what are sometimes called -1 form symmetries in certain. So these are the structures we're going to study, and we're going to study what their anomalies mean and how they can show up in cat physics.
Sorry, I guess here you have in mind that you are other symmetries, and omega depends on the background for other symmetries, right?
That's correct. All right, cool. Okay, so the primary tool we're going to be using are called mapping torus constraints. So the setup is we're going to consider some d-dimensional quantum field theory, which I'm going to write as T, and we're going to put it on some d-dimensional Euclidean manifold, which I'm just going to write as M. And we want to take, and in this talk, I'm only going to consider higher form global symmetries. And so here I want to say that this theory has this total G global symmetry, which is a product of the zero form, P form, and a D minus P minus 2 form symmetry. And I want to take these to all be discrete and abelian. And let's consider the case where there is an anomaly, which is given by some D+1 characteristic class in terms of, that is written in terms of the background gauge fields for these G0, this symmetry group G. And so what the anomaly means is that if you consider some gauge transformation of these background gauge fields, the partition function changes by a phase. And that's given in terms of this omega D+1. Yeah, so I'm not going to explain what this upper one means, but because it's not going to be very important. But the point is that if you can actually activate this phase if you look at coordinate independent transformations of your theory. So for particular types of anomaly, you can actually just do a global G0 form transformation, and that will change the partition function by a phase. And that particular phase can be realized by just integrating this characteristic class on what's called a mapping torus. I'm writing down here. No, I don't. Okay, well, here is this idea of the mapping torus. And so the idea is you have some G bundle over your manifold MD, and you're taking this on MD times an interval. And then what you do is you sort of glue together the ends of this interval with a flat G0 transformation on the G bundle. And what's special about this is that the gauge fields are actually invariant under the G transformation. So if you look at the formula for the variation of the action, the variation of the partition function, what you find is that the partition function is equal to itself times this phase. And so what that means is that either the anomalous phase has to be trivial, or that the partition function itself is 0. And this is actually an incredibly strong constraint that we're going to extract a lot of physics from. And this is what we call the mapping class, mapping torus constraint. Okay. So what we want to ask is, when does our UV quantum field theory flow in the infrared to some topological quantum field theory? And one of the great things about all the—
Sorry, could you just summarize again when that sort of thing happens?
Yes.
When you get this anomalous phase, is it just this standard sort of anomaly that usually requires a background? Your background is, are you just rephrasing a standard anomaly?
Yes. Yes.
Okay.
Okay. Very good.
So you say mapping torus, but it doesn't do anything to the coordinates, right? It just does something.
That's right. It's only a transformation of the G bundle in this case. We will actually talk about something where it's a transformation on the coordinates later, but any more questions? Okay. Right. Good. So we want to consider ask when a quantum field theory could flow to a gapped phase, which is, in other words, a TQFT. And what's great about all of the recent developments in the maths community about topological quantum field theories is that TQFTs have been studied not quite to death, but they've been studied very, very intensely. And so really all you need to do is to find some manifold in background gauge fields and prove that if you can prove that this partition function is non-zero and it has this anomalous phase, then the quantum field theory just cannot flow to topological quantum field theory. Under whatever conditions you could find that this partition function is non-zero. And what this does is it allows you to generally rule out an infrared gap phase. And this is why it's referred to as symmetry enforced gaplessness, because the other option you can have is that the theory is gapless. So now I want to review what is done by Cordova and Omori on discrete higher form symmetries. So again, we're just taking so let's consider a unitary quantum field theory, which has the same symmetry we were looking at before. And let's again call this a discrete and abelian symmetry. And so in a TQFT, what we want to do is we want to look at states that are given that are sort of defined by the partition function on an open manifold. So here I'm just going to write state, which I'm generally going to write as M rather than in terms of a picture. And it's just given by evaluating the partition function on this open manifold. And what it does is it creates a state in the Hilbert space, which is defined on the boundary of this manifold M. So unitarity, or in this case, I'm just assuming reflection positivity, tells us that for any non-zero state M, it has to have a non-negative norm. So in particular, since you can decompose the D sphere into 2 copies of the D disk, it always has a non-zero partition function. And then you can also use the fact that the sphere can be decomposed in different ways. You can decompose it in terms of a sphere times a disk, and you glue it together with a different disk times a sphere. And using the fact that the partition function for the D sphere is greater than 0, you can show that this inner product of these two states is also greater than 0. And so therefore, both of these states have to be non-trivial states. So by using this logic, you can show that the partition function on a product of two spheres is also greater than 0. So now what you want to do is you want to prove that when you are on this product of spheres and you turn on background gauge fields, that the partition function is non-zero for a TQFT. So now we want to use the fact that turning on background gauge fields for a higher form global symmetry is equivalent to inserting symmetry operators, which I'm going to call U sub G and V sub H for the P form symmetry and the D minus P minus 2 form symmetry. And so it was shown in this paper by Cordova and Omori that, in fact, this partition function is non-zero. And the sort of logic of how this works is the following. So if you have a symmetry that's not spontaneously broken, which, in other words, it's preserved, and a gapped or a topological quantum field theory, that means that the symmetry operators have to act trivially. Because if you have a non-trivial operator, sorry, this is also for a P-form symmetry where P is greater than 0. If you have a topological operator, then it will then the symmetry is spontaneously broken. So, but then if you have trivial operators, what that means is actually you can end them topologically. They can be cut and then sort of contracted to a point. And so this is sort of how their proof goes. So then what you do is you use the fact that you can sort of cut holes. Oh, yes. Oh, yes, please.
So I don't get that. It's easy. So operators act on what in this argument?
Good. So I'm assuming you have a P-form global symmetry, and acts on potentially acts on a P-dimensional operator. But if you have a P-dimensional operator in your topological theory, then essentially the symmetry is spontaneously broken because you can take that topological operator, wrap it on a trivial surface, and it'll have a non-vanishing expectation value because you topologically shrink it. And that's the same thing as saying there's a charged operator which has a non-zero expectation value, which is one of the definitions of the symmetry being spontaneously broken. And so actually, this statement was also used by Yuya yesterday. They're saying that if you have a, he was saying that when you have a preserved ZN1 form symmetry in a TQFT, then the symmetry operators, which were these Tuft surfaces, the Tuft surfaces, which essentially can be ended topologically, and that was the sort of perimeter law Tuft operator that he was looking at.
Sorry, another question. So, do I understand correctly that you have to make an assumption here that a symmetry is not spontaneously broken?
That's correct. Yes. And so the idea is that and this, sorry, essentially what we're doing is we're sort of mapping out all this possibility tree. So we're saying that we're sort of saying, well, we don't know how to talk about gapless stuff, so we're going to talk about gap stuff. And then maybe we don't know how to talk about spontaneously broken, so we're going to talk about the symmetry preserving vacuum.
I think it's a bit misleading to say the symmetry operator actually because the symmetry can act by fractionally.
That's
Trivially with everything, but it can still act non-trivially, like fractionalization.
that's true.
I don't think it's correct to say the symmetry operators are trivial. The symmetry operators are non-trivial, just that there are no other operators that break non-trivially with the symmetry.
That's correct. Sorry, I'm unsure if I think the dimensions of these symmetries might be constructed so that you can't have fractionalization. But I would have to.
You can always have, well, yeah, you can always have fractionalization.
Yeah, let's talk about it afterwards. I think that's interesting. It's also going to be related to the spin G symmetry structure. Yeah, what's up?
If there's a fractionalization, then can the symmetry operator still be opened up topological?
Oh yeah, so I think maybe that's maybe it just means that if the symmetry operator are doing that like gap boundary, right? I think maybe that's the true statement. Yeah.
Maybe a related point. Are you also assuming that these symmetries do not form an higher group structure?
Yes, yeah, it's just a pure higher form global symmetry.
In that case, I think you cannot really open the defect because you will get some phase when you intersect the defect stem. Phases or other
Wait, you said
defects.
not, you're assuming there is no higher form, no higher group structure.
Yeah.
There's no higher group structure.
Now, if there is an higher group structure,
I'm assuming there is no higher group structure, only higher form global symmetries. So, yes. I think, yeah, well, okay, I have nothing to comment on with that, except that it's a good open problem. Yeah, so the way the proof goes then is that if you open these operators, if there's no sort of fractionalization, then what you can do is construct these operators to a point, which is a local operator, and in one of these TQFTs, you assume that there's only the identity is the unique local operator, and then you can show that the partition function is proportional to the partition function with the background gauge fields turned off. And then you use the fact that there's a group-like symmetry to prove that the absolute value of this proportionality constant is non-zero, so that for a generic TQFT with all of these extra assumptions baked in, the partition function on this product of spheres is non-zero. So so good. So now that we've shown that the partition function is non-zero, if this anomalous phase is then non-zero, then what you could show is that the theory that you started with cannot flow to a gapped TQFT with a symmetry preserving vacuum. And this is what's shown in Cordova and Armory. So now what we'd like to do is to generalize this framework to include spin G symmetry structures. So again,
So.
Yeah.
So you put the theory on a very special manifold.
that's correct.
Suppose I have an anomaly that cannot be detected, for example, by mapping torus. Then can you say anything about those anomalies?
Not that I'm, I think there is work in, oh,
Sorry, I think there's a theory of things called SKK invariant, Schneiden-Claden, something else. And there was a sort of relatively recent paper which shows that basically every Bordism class, with some assumptions, does correspond to a mapping torus. So I think actually probably all cases are covered.
No, that's not true. No.
No, sorry, mapping torus plus something else. I can't remember what something else was.
All the other ones, I don't know. At the end, right? Like.
Yeah. But there is some result.
so I think there's a lot of interesting open questions. For example, what the something else is. Okay, good. So now let's talk about spin G anomalies. So again, a spin G, a theory has a spin G symmetry structure if the G bundles that you can couple to the theory can be twisted with the Lorentz group by this Z2. And so what this means is that all states in your theory have a spin charge relation. What it means is that all fermions in your theory are transformed under non-trivially under the Z2 subgroup of the center of G, and all bosons transform trivially under the Z2 part of the center of G. And so what this means is you can put your theory on a non-spin manifold, even though the theory is not bosonic. And you do that by essentially coupling to passing from a G bundle to a G mod Z2 bundle, and you restrict yourself to bundles that have a specific obstruction class, which are fixed by the second Stiefel-Whitney class of your spacetime manifold. And since we've already talked about all of these anomalies that can be captured on spin manifolds, I only want to focus on ones that are of this particular type, which are only activated on non-spin manifolds. So in order to use this mapping class torus constraint, what we need to show is that with some assumptions, you can show the partition function of a TQFT with background gauge fields turned on is non-zero on a non-spin manifold. And then if you can show that this partition function is non-zero and this anomalous phase is also non-trivial, then you can show that the theory must be gapless. And so what I want to do is restrict to the case where a four-dimensional theory with only a 0 and a 1 form of symmetry, and I want to restrict to pick this spacetime manifold to be CP2.
Sorry, I'm not understanding the step now. So are you now in a situation in which you already checked that there are spin manifolds on which the QFT can have zero partition function, then you say, okay, let's check a non-spin manifold. Otherwise, I don't understand why do you want to go to non-spin manifold?
Well, so to activate this anomaly, you need to be on a non-spin.
Oh, okay, you have an anomaly involving W2. Okay, sorry.
Yes,
Sir.
yeah.
Okay.
Yeah, good. So, just using the previous results of Cordova and Omori, all you need to show is that the partition function on this non-spin manifold with the gauge field turned off is non-zero. Because you can use the exact same sort of punching a hole and then contracting argument to turn on a higher form global symmetry that has no fractionalization. Okay. So now we're going to use, now we're going to use some nice tricks. So first, I want to use what's called the Gluck twist. So one way to construct a non-spin manifold, which is this, I'm going to look at the CP2 glued together with the reversal CP2 manifold. So one way to construct this is you take 2 copies of S2 times the disk, and then you glue with a twist by -1 to the F. So this is really nice, and this is an old construction by Gluck, and this was more recently used by David Reuter to show that essentially to derive the result we want. This twisting in the I guess the topology corresponds to a twist operator in the topological quantum field theory. So what this means that is all you need to show is that what you need to determine is sort of when this twist operator acts trivially on the Hilbert space on S2 times S1. And then if you can show that this twist operator, or determine when this twist operator acts trivially, then you would say that the fact that the partition function on S2 times S2, which is what you would get if this was the identity operator, using the fact that this is non-zero, you would be able to show that the partition function on this other manifold is non-zero. And then since you can use some sort of cutting and gluing argument to show that this also implies partition function on CP2 is non-zero. So in summary, all you need to show is that, or determine is when this twist operator is trivial, and if it's acts trivially, then you can infer that the partition function on CP2 is non-zero. So this twist operator being trivial on the Hilbert space is actually a statement about symmetry fractionalization. So symmetry fractionalization is sort of an old, well, I guess it's not that old, but it's becoming an older topic now. But in this case, it's going to be the case when line operators transform projectively under a zero form global symmetry. So from the physics perspective, this is actually also a very old story. It goes all the way back to some papers by Jakiv and Rebbe. And so this happens, for example, if you have a SU2 gauge theory with fermions. And then what you can have is that monopole lines can actually acquire a charge under this zero form global symmetry due to their interactions with the fermions, or really from fermion zero modes. And something about fractionalization is that the only sort of robust data about symmetry fractionalization is this fractionalization class, which is a H2 class, which I'm going to write as C2. And the reason why it's only the only data you have is this C2, this H2 class, is because in general, in quantum field theory, you can sort of dress all of your operators by local counter terms. And what that does is it allows you to shift the representation of a given line operator by a proper G0 representation, but it sort of doesn't mess with the projectivity, if you will, of the representation of the line.
Assuming now the one form symmetry is U1.
No.
Then I think you should replace the coefficient with the.
Yeah, you can take this against proof. Yes, I want the H2 BG0 with proper.
I mean, it might be that that group is 0 even if the one with different coefficient is not.
Yes.
You don't have to take U1, right? Like if you have Zn anyons, then you should take Zn.
Yeah, yeah, that's right. Yes. Okay. But so yeah, so more mathematically, what's going on when you have one of these when you have symmetry fractionalization is you can think of this in 2 ways. You can either think of dressing junctions of zero form symmetry defect operators by a one-form symmetry defect operator, which is determined by the fractionalization class. Or you can think of saying, or you can just say that these line operators actually have a world volume anomaly, which is determined by this fractionalization class. Yeah. So good. So for bosonic theories, you can then say that this twist operator is trivial if there's no symmetry fractionalization. And what this means is that there's no IR fermions. This is a result by Reuter. And so if you have a bosonic theory, then what you can say if there's an anomaly that's activated on CP2 is that you can only flow to a gapped phase, but if you have, you can flow to a gapped phase that is symmetry preserving only if there is symmetry fractionalization for the spin structure. So, but more generally, we want to consider spin G symmetry structures. And so then what you do is you sort of modify the story by taking a different twist operator. So in addition to twisting with -1 to the F inside of the Lorentz group, you're also going to twist with -1 inside of your zero form symmetry group. And what this does is it activates a G0 bundle in addition to going to this non-spin manifold. You can show this using it's a clutching construction. And so then you sort of follow the exact same argument, and you can show that the partition function on CP2 is non-zero only if this twist operator acts trivially, which is to say that there's no spin G fractionalization. And so what this means is that in the infrared, there are no fermionic states that are invariant under this -1 in the zero form symmetry group, and no bosonic states transform non-trivially under this -1 in the symmetry group. So then if you have these sort of generic spin G anomaly, what you can rule out is a gapped symmetry preserving vacuum without spin G fractionalization. So essentially you're stuck into this spontaneous symmetry breaking or symmetry preserving with a symmetry fractionalization in the infrared. Yeah, so there's some very nice, interesting theories that have these sort of anomalies. And one of them, for example, is a confining gauge theory, which is four-dimensional SU and Yang-Mills, 4n plus 2 Yang-Mills if you'd like, with two adjoint vial fermions. And this theory has a symmetry structure because there's a SU2 flavor symmetry that rotates the two fermions into each other. And then there's a one-form symmetry, which is the center symmetry of the gauge group. And as it turns out, this theory has an anomaly exactly of the sort we're talking about. And you can show that the partition function actually transforms non-trivially under a zero-form symmetry action, which I don't want to describe to you. But the point is that you can show that this anomalous phase is activated on CP2 and that the partition function picks up this phase. And so what you can show is that what this implies is that there's no symmetry preserving gapped phase without symmetry fractionalization. And what this means then is that if the theory can be matched either by a gapless theory, it can be matched by a theory that has some one form spontaneous symmetry breaking, and it would have some sort of action that looks like this. Or it can be matched by a symmetry fractionalization, a theory with symmetry fractionalization, which would look like this. So here the difference is I've sort of swapped this W3 and B2 to go from here to here. And the point is that in this theory, the Wilson line is charged under the UV one form symmetry, whereas here it is a fermion.
Sorry, shouldn't we expect symmetry breaking of the symmetry that acts on the two adjoint vial fermions?
Actually, I was about to say that. What we expect is that this is a gapless theory, actually.
Matched by means the infrared theory, so the long distance behavior.
Yes, that's correct. Yes. Okay, good. So now I want to talk about flux anomalies. So there are also anomalies that are only activated on discrete flux backgrounds. And so to say exactly what I mean, I want to sort of take a more general So imagine you have a theory which has where all the fields transform under this script G. So here there's some sort of gauge group, there's some sort of global symmetry group, and then there's some discrete identifications. So you can sort of generically break this up as into parts where that only act on the gauge group, only act on the sort of yes, they're often called flavor symmetry group, the zero form symmetry group, and then there's sort of parts that are identifications between the two. So this gamma G, which only acts on the gauge group, are all one form global symmetries. This gamma sub F, which only acts on the zero form symmetries, will allow you to turn on what are called flavor flux backgrounds. So for example, if you have fields that transform under an SON symmetry, you can turn on a Z2 discrete symmetry, discrete flux in the SO flavor symmetry group. And then this gamma, which sort of identifies part of the gauge group as part of the zero form symmetry group, is what I want to call center flavor symmetry, a center flavor symmetry structure. And that allows you to turn on a discrete flux simultaneously in the two. And this last one is kind of interesting. It's been studied much in the past in different communities, and it's been sometimes called center flavor symmetry because it kind of feels like a one form symmetry, but it's not. Anyways, so some of the anomalies are only non-trivial if this W2 of gamma or this W2 of gamma F is 0. This seems a bit abstract, at least for physicists. So I want to give some interesting motivating example. So one of the biggest things that energy physicists are interested in are understanding confinement and 4D chiral gauge theories. So there is one really nice class of chiral gauge theories, which are called symmetric well, I guess they don't really have a name, but they have matter content of this form. So here there's some sort of SUN gauge theory, and then you have all of the fermions transform, and it has fermions that transform under these representations of the gauge group, and then you have some sort of zero form symmetry that these fermions transform under. And what's really interesting about this is that if you add this 4 fermion interaction, all of the preserved symmetries, well, almost all of the, until recently, it was thought that none of the symmetries were anomalous. You can check there are no perturbative anomalies, and sort of all the old non-perturbative anomalies are non-zero. And so what was proposed is that this theory confines, where these two fermions sort of combine into sort of like a proton, if you will, and then, which I'm going to call this capital psi, and then this 4 fermion interaction really becomes the mass. So the proposal is that since there are no anomalies, this interaction, which is the sort of minimal thing you can write down, will trivially gap the theory.
Sorry, is this full fermion interaction a dangerously relevant operator then?
I don't believe it's no. That's why it's interesting.
So why, I mean, perturbability is an irrelevant operator.
Yes.
So you're saying that it's modifying the dynamic at.
Yeah, this is part of the proposal, is that essentially if you think that the theory confines in this way, then if you just naively plug this in, it looks like a mass term. And the theory would then be a trivial gaps theory, be a free massive fermion. So that's the proposal.
You need to put some assumption about the scales, right? Something like
Yes.
the scale of M should be much smaller than the scale of confinement.
Yes. Yeah. It's true. So this is that is the proposal. This is sort of the cartoon version of the proposal. Right, but this theory actually has both has this min G symmetry, and it also has this center flavor symmetry structure. And in fact, what you can show is that this theory has a discrete anomaly, which involves only the spin G structure and the center flavor symmetry structure. So in a sense, it has an anomaly of things that are not symmetries. It's a bit bizarre. And of course, when you see an anomaly, you know that the theory just automatically cannot be trivially gapped. But we want to ask sort of what else can we say about it? Just to say, throw up your hand and say, oh, it can't be trivially gapped. It's great, but the whole point of these anomaly enforced gaplessness constraints is that you can actually say more. And so again, what we want to do is just to show that the partition function is not equal to 0 with the appropriate fluxes turned on. And so now what we can do is we can twist additionally by -1 in the gauge group and by -1 in this zero form symmetry group, which I guess I'm calling a flavor symmetry. And this corresponds to a twist operator in the TQFT. And then what you would say is that what this means then is that the partition function on CP2 with all of the appropriate fluxes turned on is non-zero if the twist operator acts trivially on the Hilbert space. And so then again, this means that the twist operator is only trivial if there's no symmetry fractionalization. So back to our example, since this theory has this W2, W3 type anomaly, this can be activated on the mapping torus, much in the other example I showed you. And so what this means is it can only flow to a gapped phase if there is some sort of symmetry fractionalization. And you should have already known by the anomaly that it cannot be trivially gapped. So in other words, the proposal for this flavor of theories doesn't work. So this is, I guess, something I already said, but it is kind of interesting that there's these turning on a W2 or going onto a non-spin manifold is not really a symmetry. And similarly, turning on discrete fluxes is itself also not really a symmetry. It's just something you can do. And it's kind of interesting that you can actually gain insight into your theory from these symmetry structures, even though they're not really themselves a symmetry. And so I guess one of the points I wanted to make in the talk is to emphasize that some of these symmetry structures still have some interesting physical contents that you can use to constrain the dynamics of a theory. Yes.
Can you see the topological operator which can be cut open? Like you enlarge your symmetry to be some symmetry which does not act on anything. Then you can put a mesh of operators.
Let's talk about it afterwards. This is actually something I'm thinking about right now with Custis. Good. Okay. We're doing really well in time. Okay, so now I'll tell you about this other part that I was prepared to skip. This is something recently I've been working on, which is sort of a different flavor.
Since you're changing topic, can I ask a question? A general point is that is there some assumption that RG flows are the same on manifold in the sense that how can you say, for instance, in principle, that anomalies that can be detected only on non-spin manifold if the consequences for RG flows on manifold on spin manifolds? It's obvious. It's an assumption.
Yeah, I think it's obvious. I think you would say, well, I guess all of the TQFTs I know that you would use to try to demonstrate, to match these anomalies are some sort of discrete gauge theory. And then these W2s are just sources. Essentially what you're doing is you have some infrared theory with some symmetries. And you're just saying, I can match this flux to this one to this one. And so it really just tells you you have to have some non-trivial theory. And the fact that it's a non-spin manifold is just activating a flux in theory.
Can I follow up maybe? Do you know of any TFT that cancels this anomaly but it becomes trivial in spin manifolds? There's a W2 of TM.
I do not. The only ones I know are, I didn't write it down. It was actually showed up in this last example. These types of TQFTs, which is just the Z2 gauge theory, and I mean, I think the fact that you, I think the point is that like by studying the partition function, you know that there has to be some fermionic line or some sort of fractionalized line in your theory, and that's irrelevant to what manifold you're on. It's just some operator in your theory. I think that's why I was saying I think it might be obvious.
Just wanted to say that the next talk is at 12, so if you feel like finishing early, that would be.
That was actually, that was my plan. Don't worry, this part's actually only 2 slides because I to go quickly. Okay, anyways, so I'll just plow ahead really quickly then. So coupling constant anomalies occur when you have a continuous family of theories. So imagine you have some theory T and it's indexed by some periodic parameter theta. And we want to consider such a family of theories that is symmetric under some symmetry. And so what you can have is that as you go around the parameter space, the partition function can actually pick up the phase. It would be a non-trivial line bundle over the parameter space. And in this case, you can say that this looks very similar to an anomalous phase from the case when you have a symmetry. And indeed, that's why we call it a coupling constant anomaly. So if this anomalous phase has some sort of quantized coefficient, like for example, if this omega d is Pontryagin square of some one-form background symmetry, then this is some sort of phase that you actually cannot cancel by a local counter term. And then using the fact that the partition function of a TQFT without spontaneous symmetry breaking is non-zero, what you can show is that for a symmetry preserving family of TQFTs, you can't actually flow to a trivially gapped phase if you have one of these coupling constant anomalies. So what that means is that you can either have a discontinuous family of theories, which is phase transition, or you can have the symmetry be spontaneously broken, or the theory can be gapless, just I guess always an option. And so maybe one interesting example, at least for physicists, is sort of one of the very first examples of this that was studied is you can take SUN Yang mills with a theta angle. So naively, theta here is periodic mod 2 pi because the Chern class is quantized. And but the theory also has a ZN one form center symmetry. And when you turn this on, you find that the partition function changes by this anomalous phase as you go around the parameter space. And this corresponds to some sort of anomalous phase, a coupling constant anomaly that can be written in this form. And so there's sort of two interesting gapped phases that match this anomaly. One is the first one is the confining gapped phase, where the ZN one form symmetry is conserved. And then, so this is actually what we think happens in the real world, is that the one form symmetry is conserved, and then the anomaly, and then the theory is sort of trivially gapped, except for theta equals pi, where there's a phase. However, this theory, the anomalies of this theory can actually also be matched by a ZN gauge theory of this form. And this is the case where you have the one form symmetry breaking. And what's actually interesting about this is that this theory you can get from a very simple quantum field theory called the Abelian-Higgs model, charge n, with a theta term. So, and it actually turns out all of the anomalies match the Yang-Mills, including the time reversal symmetry anomaly. But anyways, so I'm pretty much done now. And I just want to emphasize some of the sort of general lessons that, or not just lessons, but the general points, is that if you can prove that there's some correlation function of topological operators in a topological theory that's non-zero, and there's some sort of anomalous action on this correlation function, then you can say something interesting about RG flows generally. And it's also kind of interesting that you still have consequences of anomalies for different types of symmetry structures in a quantum field theory, such as the spin G structure, this sort of center flavor symmetry structure, and coupling anomalies. And there's just a lot of open questions that I think would be really interesting that you could ask, like, for example, what happens if you have a higher group symmetry? What happens if you have a more general categorical symmetry? And you could also ask, is there anything else you could learn about theories from generalized symmetry structures in quantum field? So with that.